All right, hello everyone. So in today's lecture, the objective is to derive Kepler's time equation that will allow us to do the mapping between the true anomaly and time. And as I said previously, the way to do it is to first derive the equation that will relate the true anomaly to the eccentric anomaly, which is a new variable that we will introduce today, and then do the mapping between the eccentric anomaly and time to ultimately merge the two together and go from time to true anomaly or vice versa. Okay? So we had already related true anomaly to time for the circular orbit. So let's now have a look at elliptical orbits and see how we can do the mapping. Okay? So let's first introduce the new variable I was talking about. So let's go over here. Let's draw an elliptical orbit, obviously. Like that, in red. Here we have our M1 at a focus of this ellipse. And then what we'll be doing is that on top of the ellipse, we're going to draw a big circle that has a radius equal to the semi-major axis of the ellipse. In other words, if you were to locate the center of the ellipse right here and realize that this side here has a length of A, semi-major axis, that means that we're going to draw a big circle, the radius equal to semi-major axis. Something like that. Well, pretend that the blue thing I just did was a circle, because obviously it didn't look like a circle. But okay, this is meant to be a circle that encloses the ellipse inside of it. Okay? So again, the radius of the circle is equal to A, or if you will, equal to the semi-major axis, like that. Okay? So now if you have, say your spacecraft is orbiting around and happens to be somewhere over here, you know that the distance between the spacecraft and M1 is small r like this, and that this is here the true anomaly angle between the eccentricity vector that points always at the perigee of the orbit, which is in red, like that. So what we're going to do is that to define the eccentric anomaly, we're going to draw a line vertically from the spacecraft position up and down like this, such that it meets the line of semi-major axis here at the 90-degree angle. Okay? Just going to remove the 90-degree angle symbol to not clutter too much the figure. So the eccentric anomaly is the angle between the center of the ellipse, which coincides with the center of the auxiliary circle. And then what you're going to do is draw a line all the way up to where this vertical line that was going through the spacecraft position intersects now the blue circle. Okay? And the angle that this big line draws with respect to the major axis here is your new angle denoted by capital E and called the eccentric anomaly. Okay? And we shall denote this big radius vector between the center of the ellipse or the center of the circle all the way up to where the vertical line intersects the circle as capital R. Okay, so you have, as per before, the distance between the spacecraft and M1, small r. Draw a line vertical through the spacecraft at 90-degree angle from the major axis. And then where that line intersects the auxiliary circle, then draw another line from there all the way down to the center of the ellipse, the center of the circle. And then this angle happens to be your eccentric anomaly. And I'm going to call this side here capital R. Hopefully it's clear. Okay? So what we're going to do first is to have a look at the geometry of the problem here. And we're going to say that this side here, from the center of the ellipse all the way to where the vertical line intersects the major axis, is actually capital R cos eccentric anomaly. Okay? So just this guy here. This is capital R cos eccentric anomaly. Then we're going to say, okay, this plus this extra little side that goes from the end of the first one all the way to M1, the focus of the ellipse in green, is going to be pi minus theta, which is this angle here in green, right? The complementary angle to the true anomaly would be pi minus the true anomaly, the angle in green here. And then I'm going to say cos of that times this here, which is small r, will give us that small side. Okay, so we're just focusing our attention on this triangle here, in other words. Okay, so r cos of this angle give us this little side in green. So, and then if we add both together, the first segment here in black plus the second segment here in green, then what we're getting is the total length between the center of the ellipse all the way to a focus of the ellipse in red, like that. Okay? Yeah. So we're going to say the black segment plus the green segment equal to both together, which is actually A times E from before. Remember the when we talked about elliptical orbits a couple of lectures ago, we had said that the eccentricity was equal to C over A, where C was the distance between the center of the ellipse to either foci, such that we could now say that C is equal to AE, where C is actually this side here in red. Okay? Now, another thing we can do with that equation is to realize that, well, the radius of the big blue circle, the auxiliary circle we had drawn over the ellipse, is actually the semi-major axis, right? As shown here. The radius of the blue circle is the semi-major axis anywhere or everywhere. So that we can come back here and replace R with just our semi-major axis like that. Okay, so what we're going to do next is solve that equation for the term in black. So A cos eccentric anomaly is equal to A E minus R cos pi minus true anomaly. Turns out that minus cos pi minus theta is the same as just plus R cos theta. And this gives us semi-major axis cos eccentric anomaly. So all these relationships were derived from the first one and were obtained just by looking at the geometry of the problem here and doing a bit of trigonometry. Okay, nice. What do we know about R? Can we express R in terms of true anomaly and semi-major axis? The answer is yes. And that is done through the orbit equation. So we're going to say that A cos eccentric anomaly is equal to AE plus, either you could use P over 1 plus E cos theta for the orbit equation, but here I want the version that has a semi-major axis on the top instead of just P. I'm using that version of our orbit equation. And then cos theta. So just reporting this term here at the end of that equation. Okay? So what we'll do next is to solve that last relationship for cos of the eccentric anomaly. So I'm going to write cos eccentric anomaly equal to AE divided by A is just eccentricity plus 1 minus E squared over 1 plus E cos theta times cos theta. Next up, I'll just distribute my cos theta inside this parenthesis to write cos eccentric anomaly equal to eccentricity plus cos true anomaly minus E squared cos true anomaly. All this being divided all this here divided by 1 plus E cos theta. Next step, so all I'm doing here essentially is playing with the right-hand side of that equation to give us a nice and neat relationship for cos of the eccentric anomaly, okay? So next up, I'm going to put everything onto the same denominator. So 1 plus E cos theta, which will become E plus E squared cos theta for this, plus cos theta minus E squared cos theta. That's convenient because now we can cancel the E squared cos theta terms. To rewrite that as E plus cos of our true anomaly over 1 plus E cos true anomaly. And all this was for cos eccentric anomaly. All right? Now that I have this result in the digestible form over here, what I'll do is that I'm going to take that, I'm going to say 1 plus cos eccentric anomaly. And you'll realize the reason why I'm doing this extra step at the very end, later on during the development process. Okay? So I'm going to write it in red because this is kind of a final intermediate result that we need towards the development of Kepler's time equation. I'm going to say 1 plus E plus cos eccentric anomaly equal to 1 plus E cos theta plus E plus cos theta over 1 plus E cos theta. Okay? So I just added 1 plus this, and I've done everything on the same step, so I put everything onto the same denominator in one step. Okay? So I'm going to keep that result handy for later on. So we can erase this. And now we can use a property of ellipses embedded into circles, just like that, to say that the ratio of semi-minor axis over, let's switch back to black, the ratio of semi-minor axis, which is B, over semi-major axis A is equal to small r sine true anomaly over A sine eccentric anomaly. Or essentially the ratio of this over this is equal to the ratio of this one in green over the big one over here, okay? And that follows at any point along the ellipse/circle combination. Fantastic. Now I can pull this on this side, cancel the A's to say that B sine eccentric anomaly is equal to R sine true anomaly. And I'm going to focus on the left-hand side of that relationship. And furthermore, I'm going to replace the expression for B for what we had derived in the elliptical orbit subsection, which is A square root of 1 minus E squared. So all this is for B. Put that in parentheses, multiplied with sine of the eccentric anomaly, then equal to R sine theta, which is our true anomaly. Okay. So you saw what I did previously here. I had first solved for cos of our eccentric anomaly and played with the right-hand side of that equation till I obtained something that was kind of neat. So here I'm going to do something similar, but instead of solving for cos eccentric anomaly, I'm going to solve for sine of the eccentric anomaly. Okay, so I'm going to solve for that term. So sine eccentric anomaly equal to R sine theta divided by A times square root of 1 minus E squared. And then I'm going to use the exact same trick as before, and that is to replace R with the orbit equation given in terms of semi-major axis and eccentricity. So I'm going to replace this term with my orbit equation to be able to write that sine eccentric anomaly is A times 1 minus E squared over 1 plus E cos theta. So all of this is for R, then times sine theta divided by A times square root of 1 minus E squared. And from there, I'm just going to keep playing with the right-hand side of that equation until I obtain something which is similar to this. So only function of eccentricity and true anomaly to make my life easier eventually. So from there, well, I can cancel the A's, obviously. I can what can I do? What can I do? I am going to rewrite this term as square root 1 minus E squared square root 1 minus E squared sine theta over 1 plus E cos theta times square root of 1 minus E squared. Yeah, that's what I want to do, such that now I can cancel those two square roots together and just write that that would be square root of 1 minus e squared sine theta over 1 plus e cos of my true anomaly. Okay, so I'm gonna stop here for sign of eccentric anomaly. This is satisfactory for me. So next up, what we have to do is to use the half angle trigonometric identity that says that tan of an angle over 2 is equal to sine of said angle over 1 plus cos of the angle. Okay? So if you apply this identity, and well, to our case, where our angle happens to be eccentric anomaly instead of a generic angle x, we can then write that tan of eccentric anomaly over 2 is equal to sine eccentric anomaly over 1 plus cos eccentric anomaly. And now you see why previously I had solved for 1 plus cos eccentric anomaly and then sine eccentric anomaly. Well, that is because I want to use that identity at this point to keep simplifying the right-hand side of my relationship. Okay, so let's apply it and let's see what we end up with. So we're going to say that tan of eccentric anomaly over 2 equal to sine eccentric anomaly, which is all of this, so square root 1 minus e squared sine theta over 1 plus e cos theta. All this is for the numerator. Then I need to divide this with 1 plus cos theta, or in other words, multiply this with the inverse of this fraction, which is what I'm about to do. So 1 plus e cos theta over all of the above, which is 1 plus e cos theta plus e plus cos theta, like that. Okay, so don't panic. It looks like a giant mess right now, but we're going to keep simplifying it until we get something very nice. Okay? So right away, we can say that we can easily cancel those two terms and just rewrite it as square root of 1 minus e squared sine theta over. So here on the denominator, what I'm going to do right away is to factor out my cos theta out of those two terms to write 1 plus e plus cos theta that multiplies e plus 1. Okay? And now I'm going to keep playing with my denominator here to rewrite it as I'm not touching the numerator on the top. This, in my denominator, I'm going to factor out 1 plus eccentricity, so 1 plus e. So 1 plus e times 1 times plus cos theta. Okay? Just like that. Okay, so now, do I need the figure again? I don't think so. So let me erase it. So now I'm going to shift my attention to those terms that look kind of similar, the 1 minus e, the 1 plus e, and rewrite them slightly differently such that I can ultimately cancel them out together. So here, we're still talking about tan of eccentric anomaly over 2 equal 1 minus e square root of can be replaced by the square root of 1 minus e times square root of 1 plus e. All this still multiplies sine true anomaly divided by my 1 plus e could be split into square root of 1 plus e, square root 1 plus e, times 1 plus cos theta, 1 plus cos theta here, like that. And now we're almost at the end of this process, which was again to relate the true anomaly to the eccentric anomaly, if you remember. So you see on this side we have eccentric anomaly, and over there we have our true anomaly terms. So we'll just keep playing a little bit more to simplify the right-hand side. So first off, we can cancel those two terms and write that tan eccentric anomaly over 2 is equal to square root of the ratio of 1 minus e over 1 plus e, like that, times sine theta over 1 plus cos theta. Okay, so look at that equation. Think about what you would do to further simplify it while I take a sip of green tea here. Okay? So, you're right. The next step is to swap out this term here, which is sine theta over 1 plus cos theta, using the half angle trig identity. And that is just to replace it with tan of theta over 2. So ultimately, we say that tan of eccentric anomaly over 2 equal to the square root of this ratio here, which is only a function of the eccentricity of the orbit, times tan of true anomaly over 2, like that. I'm gonna box it in red because this is the end of step 1 out of the 2 steps that we needed in order to relate the true anomaly to time. Because if you remember, the step-by-step procedure said that in the first step, we wanted to relate true anomaly to the eccentric anomaly. Congratulations, we've done it. And then in the second step, we'll see how can we relate the eccentric anomaly to time, and then merge those two to relate true anomaly to time. Okay? And the result of the second step, that is to relate eccentric anomaly to time, will give us the so-called Kepler's time equation. So as you can tell, this is much more tedious than the circular orbit situation, where the relationship was quite straightforward, and the reason was that the mean orbital motion was directly related to the true anomaly rate of change, because it was the position vector swaps out the orbit at a constant angular rate for a circular orbit, but for an elliptical orbit, that's not the case anymore. So that's why we have to go through these multiple extra steps here. If you want, you can also do the inverse of that result here and just write tan true anomaly over 2 equal to square root of the inverse of that, so 1 plus e over 1 minus e, times tan of eccentric anomaly over 2. Both relationships will come handy in future. So it's good to know that you can just flip it upside down to get theta function of eccentric anomaly or vice versa. Okay, so that was step 1. Now in step 2, again, the objective is to relate eccentric anomaly to time. And again, that will be done through Kepler's time equation. Okay, so to do that, let me draw an orbit. Highly elliptical, that looks like a potato. So here we have M1, and now we're going to look at the area being swept by the position vector R, like that, and denote this area under the curve here as AE, where AE, again, is the area swept by the position vector that goes from the planet all the way to the spacecraft around here in some time interval. And that time interval is the time between the current time, t, and the time of perigee passage. This is the time at which the spacecraft is directly at this point, which is the perigee, as you know. So I'm going to denote the time of perigee passage by t subscript p, okay? So let me write it in words. So time of perigee passage in seconds. This is TP. This is the time at which the spacecraft ends up here. This is our current time. So we're going to say T minus TP is the time interval over which the position vector went from the perigee all the way to where the spacecraft lies currently on the orbit. Okay? So AE, just based on what I just said, will be equal to the rate at which the area is being swept, if you will. So this is AE dot times the time interval, which is T, minus TP. Okay? So that would be in meter square per second times seconds will give you meter square for the area. Now, from Kepler's laws, we know that this is actually equal to the area of the ellipse, pi AB, over the orbital period, okay, times T minus TP will give us the area swept by our position vector. We know, furthermore, how to rewrite the orbital period as function of our semi-major axis, and that would be 2 pi square root of a cubed over mu, which is 1 over the mean motion, which is this term here, and all this times T minus TP. From there, I can cancel out my pi like that. Then I can rewrite it slightly differently, such that AE is ultimately equal to AB over 2 times square root of mu over a cubed times T minus TP. Okay, by the way, if TP is the time of perigee passage and T is our current time, then T minus TP is the time since perigee passage. Okay, so I'm going to write it to make sure that you remember that time since perigee passage is T minus TP, whereas time of perigee passage is just TP. There might be a question about this in the midterm, so make sure that you know the difference between since perigee passage and of perigee passage. And pay attention to the wording in any exams or any problems that you happen to be working on. Okay, so again, AE here on the left-hand side is the area swept by a position vector over a time interval defined by T minus TP. Okay, so now let me draw the auxiliary circle, which was in blue from before. If you have the auxiliary circle that encloses the elliptical orbit inside of it, I'm not going to draw the elliptical orbit because we don't need it for this discussion. So let's just focus on the auxiliary circle now. We have the origin of the ellipse and the circle, or the center, right here. We have a focus here where M1 is the planet. We know that we have let's say the spacecraft happens to be, do I need the ellipse? Maybe not. I'll try to avoid it to not clutter too much the diagram. So this is R, which is the same as the semi-major axis A, right, from before, because this is a circle. We have our eccentric anomaly over there. Set A equal to R. This dimension from the center of the circle to the focus is AE. AE, like that. And if you go from the planet, the projection of the spacecraft along the auxiliary circle, you're going to get this vector. You know what, let's stick to A only for this side, and let's call this guy here R, from M1 to the projection of the spacecraft along the auxiliary circle. Do we have everything we need? Okay, so what we're going to do next is look at the area swept by this position vector, capital R vector, in the same, over the same time interval. So the area being swept is again the area under the curve. So this is what we're looking for, and this is quantified as AC. This is your AC. Okay? So to calculate AC, what we're going to do is look at the difference in two areas. The first one in red will be the area being enclosed by this portion of the circle altogether. And this is just pi a squared times a fraction of the entire circle, which happens to be eccentric anomaly, over 2 pi. Okay? So this is the area in red, which goes from the center all the way here, so which is defined essentially by the eccentric anomaly angle. That's this one. Well, we said that AC is just that portion over here. So we need to remove then another section of the pi, which happens to be the section in green, which is simply this triangle over here, which we're going to say that this is equal to the base of the triangle, AE, times its height, divided by 2. So base of the triangle is AE times its height, which is A sine eccentric anomaly will give us this guy here. So A sine eccentric anomaly, and then divided by 2 because this is a triangle. Great. Whew, that was a bit tedious. Hopefully you guys could see the diagram clearly in the video. But essentially, the black area, which is just this over here, is the red minus the thing in green. So you're left with that portion here. And that corresponds to the area swept by the position vector capital R. Boom, like that. All right. Let's leave it as that for now. And let's now look at the area of an ellipse versus the area of a circle. So area of an ellipse is pi AB. Pi times semi-major axis times semi-minor axis. Whereas the area of a circle would be pi times its radius squared, or A for the radius of the circle in our example here. Such that you can say that combining those two relationships, that AE, the area of an ellipse, let's say area, will be related to area of a circle, but by multiplying it with B and dividing with A. Okay, because if you take this, divide with A, you get pi A. Then multiply with B, you get pi A, B, and D. So that is the relationship between AC and AE. All right. Turns out we have AE from before, we have AC now, so then we can write, let me just use that equation on top to save some time here. I'm going to erase this diagram. We write that AE, which is this, is equal to all of that times the ratio B over A. Okay? Equal pi A squared eccentric anomaly over 2 pi minus A B and A squared B sine eccentric anomaly over 2. All of that gets multiplied with B and divided by A, such that now you have the relationship between AE and AC through that factor B over A. Okay? That side over there can be further simplified by canceling A's here and saying that that would be AB hold on a second. Let me cancel this with that, and let me cancel the pi as well. So we're left with this. So that what you have is A, B eccentric anomaly over 2 minus A squared B sine eccentric anomaly over 2 for this side. Now you can factor out the AB. Oh, I needed to cancel one of the A's here, the A that was on the bottom too. Sorry about that. So this is just A. So now you have AB. AB, I'm going to factor this out. And you write that this is eccentric anomaly over 2 minus sine eccentric anomaly over 2, like that. And all of it is equal to AB over 2. This guy here, hopefully remember that this is the mean orbital motion, or n, which is a constant, times the time since perigee passage. And obviously you can cancel the AB over 2 on both sides of that equation. Just write N times T minus TP equal to eccentric anomaly. I had an eccentricity missing here. Boom, boom. Eccentric anomaly minus eccentricity, sine eccentric anomaly, and that's it. Yeah. What we're going to do next is to define another variable, which is the mean anomaly. Oh boy. So now we have the true anomaly, theta. We have the eccentric anomaly, E. And now I just said that we're going to define the mean anomaly, which is denoted by capital M. Mean anomaly, which is equal by definition to this term here on the left-hand side of that equation. So equal to the mean motion times the time since perigee passage. With that new definition, this equation becomes then M equal eccentric anomaly minus eccentricity sine eccentric anomaly. And ladies and gentlemen, this very simple, elegant equation is Kepler's time equation. Yeah, we did it. Kepler's time equation that gives us the relationship between time embedded in this mean anomaly term, right? This is time, to the orbital position in terms of angles, in that case, eccentric anomaly. But we know we can relate the eccentric anomaly to the true anomaly, and that's what we did in the first step with the tan eccentric anomaly over 2 equal to square root of the 1 plus E over 1 minus E term, or vice versa, times tan of true anomaly over 2. And then we now have closed the loop and defined the proper relationship between true anomaly and time as a two-step process. One thing to pay attention is that whenever you use Kepler's time equation, you have to use radians for the units for the eccentric anomaly. Okay? I'm going to say it a couple of times to make sure that this is acquired and understood. So again, the eccentric anomaly has to be in radian in Kepler's time equation, or in Kepler's time equation, E has to be in radian. Always, always, always. Okay, because this is not cos or sine of an angle, which you can get away with degree on your calculator. Because the angle is on its own, you cannot swap it with degrees. That won't work. It has to be in radian to make sure that this works out. Okay? So I guess that's it for this lecture. We've been able to successfully achieve our goal for today, which was to relate true anomaly to time as a two-step process using the half-degree trigonometric identity, the tan over 2 thing, and then using Kepler's time equation to finally relate true anomaly to the time here. Okay? So I hope that makes sense to you, and let's keep learning more in the next upcoming lectures. Goodbye, guys.